Hello everyone, back again for more of Chapter 6 on simulation. We're in the Part 1, Chapter 6 slides. Go to the Will They Connect section. So here's the game. You know how it is, at least this is how I hear it is, when two young folks are kind of interested in each other. And maybe each of them has the thought that that interest might blossom into an actual romantic relationship, but neither of them really has the nerve at this point to declare themselves to one another. And so they engage in what is called a talking. So let's imagine Anna and Raj, two, say, young college students who are at that talking stage. And they make a date for coffee tomorrow at the local coffee shop under the pretext that perhaps they will study together or work on, the next computer science assignment, something like that, right? But neither one wants to appear to be too interested in making absolutely sure that they meet, because that would be kind of showing your hand. And so they don't write it into their calendars. And let's say that after making that date, both of them forget that the exact time they agreed to meet. All they can remember is that it was supposed to be sometime between 10 and 11 a.m. And so each person, independently of the other, just randomly picks a time between 10 and 11 to arrive. And the thing is, because they're just talking, and again, they don't want to be seen as being too eager to see the other person, they're each willing to wait 10 minutes for the other person to arrive. What is the chance, under these circumstances, that they will actually meet for their coffee date, non-date? So again, with our idea of modeling random processes, the process we've got to model here is that 1 hour time period. And this is going to involve getting Anna and Raj's arrival times. And let's measure that in minutes after 10 a.m. So for each person, the arrival time would be a real number between 0 and 60. So we could do a function call runif and get one arrival time for Anna, say. It's a random real number between 0 and 60. So we bound the name Anna to the result of that function call. And similarly, let's bind the name Raj to the result of a function call to runif. Now, we need to think about what are the conditions under which these two people will actually connect, will actually meet each other at the coffee shop. They're going to connect if their arrival times are no more than 10 minutes apart. So one way to think about this is that they'll connect if Anna's arrival time minus Raj's arrival time is somewhere between minus 10 minutes and 10 minutes. The minus 10 would be where Anna arrives 10 minutes before Raj, and so they would just barely miss meeting each other. The 10 is where Anna arrives 10 minutes later than Raj, and again they barely miss meeting each other, but this time it was because Anna came after rather than before. But any number between minus 10 and 10 for this difference between Anna and Raj is going to be a situation in which they meet. So we need Anna minus Raj to be between minus 10 and 10. Another way of saying that is that we need the absolute value of the number Anna minus Raj to be less than 10. So what happens this time with our number Anna and our number Raj? Let's bind them together in a little vector, a named vector with names Anna and Raj. And we see that Anna arrived 12.5 minutes after 10, and Raj arrived 28 minutes after 10. And so Anna minus Raj turns out to be 12 minus 28 minus 15.85 minutes. So clearly here, Anna has arrived much earlier than Raj. She's going to wait her 10 minutes. She's going to miss him. And that's reflected in this number minus 15. It's less than the minus 10 limit. They're not going to meet. We're looking at it from the point of view of absolute values. The absolute value needs to be less than 10, but this time it came out to be 15. They're not going to meet. So we've got the basic idea of how to model the situation once, and to figure out from the numbers that we get whether or not the pair of them meet. We now just have to think about how to repeat the process a lot of times to really do good simulation. Well, the great thing about RUNIF is that you can get lots of random numbers at once. So why don't we have Anna arrive at the coffee shop, let's say 8 times. 8's a small enough number that our results can still fit on these slides. Let's also have Raj arrive at 8 random times. So now Anna and Raj are vectors of length 8. Here's Anna's vectors. Here's Raj's vector of arrival times. So when we compute Anna minus Raj, we get 8 time differences. Let's look at the absolute value of Anna minus Raj, and we get 8 absolute values. We just need to see which of them are less than 10. And so we construct the Boolean expression, absolute value of Anna minus Raj is less than 10. And wherever this turns out to be true, that's an occasion where the two of them met. So if you want to think about the results in a table, each row in this table is a simulated coffee shop day. And in the first column, we have Anna's arrival time, Raj's arrival time. Anna arrived 18 minutes before Raj. The difference in their time was 18.52 minutes more exactly. And so Anna's going to wait her 10 minutes and leave. They will not meet. On the other hand, if you look, say, at the 5th row, Anna arrived 35.9 minutes after 10. Well, Raj was already waiting for her because he arrived at 10:32. He only had to wait 3 minutes. He's still there. When she arrives, they meet. So now that we see how the basic process can be modeled, we just need to encapsulate our work into a simulation function. We'll call it Meetup sim, and it shall be a function of several parameters. A reps parameter for how many times you want to repeat the random process. Let's give it a default of 10,000. A table parameter to say whether or not a little table of the results should be reported to the user. Let's have its default value be false. And a seed parameter in case the user wants to provide a random seed to keep the results consistent with each function call. Its default value shall be null. The user could simply ignore the seed parameter if they wish. We'll begin with our boilerplate, which will be standard when we provide the option for a seed. If the seed is not null, then we're going to set R's random seed to the seed value provided by the user. And then we begin the modeling process. We have Anna arrive at the coffee shop reps number of times. Semicolon just allows us to get another R command in on the same line. And we have Raj arrive reps number of times. And then we create a vector of our results as to whether or not they met. That vector shall be called connect, but the way it's computed is through a Boolean expression. The absolute value of Anna minus Raj is going to be a vector that's reps long, because Anna and Raj are reps long. The Boolean expression, is this less than 10, will create a logical vector of trues and falses that's reps long. Now, if the user said table should be true, we're going to get inside this next if statement and we'll print out a table of the results as to whether or not they met. And then for sure, we have a little report down at the bottom. By taking the mean of the connect vector, that's equivalent to counting up the number of trues and dividing by the number of reps. That'll be the proportion of times they met in our simulations, and that'll be the estimate of the probability of meeting. So why not teach that function to your global environment and give it a try? So in this function call, where I use the default number of reps, 10,000, and I ask for a table and I set a seed, I find that out of the 10,000 repetitions, they met 3,045 times. The proportion of times they met was the 3,045 divided by the 10,000, 0.3045. And so I estimate that the probability that the two of these people will meet is about 30%. So last couple of examples we've looked at, we've taken advantage of R's vectorization capabilities to create very quickly vectors associated with information in the modeling process, and vectors of the results of the simulations. But you also know that simulation can be done using some kind of a loop where you perform the modeling process once each time you pass through the loop. I'd like to look at that situation here with the Anna and Raj example. So does it really make a difference if you use vectorization versus looping? Here's another version of the Meetup simulation. We call it Meetup Sim 2. And it has the same interface as our original Meetup Sim, a reps parameter, a table parameter, and a seed parameter with the same defaults. But we're going to use a loop instead of R's vectorization abilities. So we're going to set up, first of all, a vector to hold our results. It's going to be reps long. I probably should have asked it to be a logical vector instead of a numeric vector, because it's ultimately going to hold trues and falses. But that won't matter for R. As soon as it sticks a true or false into a numeric vector, then it's going to do some conversion to make things all right. Now we have our for loop. For I in 1 to reps, so I is our index, and our iterable is 1 colon reps, so that is just the vector of numbers from 1 up to reps. And every time we pass through the loop, we'll make Anna and Raj pick one random time to enter the restaurant. We will then check whether the absolute value of the difference between their arrival times is less than 10. That's going to be one true or one false. And we shall say that connect at the ith place, notice the square brackets there, selecting out the ith place of connect. Connect at the ith place shall be that true or false. The result is being stored into our little results vector. So by the time we're finished with this for loop, connect is going to be a vector of truths and falses that's reps long. If the user wants a table, we'll print the table out for them, but it's certainly at the end we will report the mean of connect. That is the estimate of the probability that they'll meet. So it would be interesting to see if there's a difference in how long R takes to run each of these functions. There's fortunately a nice R function called system.time, and it computes the time to run a particular function or any group of R commands. All you have to do is wrap the function call inside a call to system.time. So we have our regular function call for the Meetup sim, but the results of that are in a call to system.time. And when I did this on my own Mac at home when I was making these slides, it took a total of 7/1000ths of a second. Most of that time was spent on that particular process, Meetup Sim. There's also a system time here. That's supposed to be the operating system doing its regular chores, like watching the mouse move across your screen or listening for, keyboard input and things like that. But that time was like nothing in comparison to what was used up in actually Meetup Sim. Now, if we try the same thing, the exact same thing, but with Meetup Sim 2 that has the loop, then we get similar results. Again, about 30% is the probability. But look at the total time. It's now up to 0.046, okay? And again, most of that is spent on the process itself, 0.042. Now, if you compare 0.007 to 0.042, you'll find that Meetup Sim 2 is actually taking about 6 times as long to do its work as Meetup Sim did. So the for loop runs a good bit slower than R's native vectorization does. So when you're doing simulation work, try to avoid looping if you know how to get your modeling done and your results recorded with some kind of native vectorization process. But don't worry too much about it, because if your job is small, like our job was there, it's not really going to make a lot of difference in time. Okay, that's it until next time. Bye-bye.